This is what really happened to Iron Man. It was a snap heard round the universe that brought this iteration of the Marvel Cinematic Universe to a close. It was the same snap that closed the book on the hero that started it all. But before we let Iron Man go, what really happened to Tony Stark? What does snapping an Infinity Gauntlet actually do to you? Avengers Endgame has already made its mark. It has smashed over a dozen box office records like a golden sword boomerang thing smashing a shiny vibranium shield from a different timeline. And it stands as a satisfying conclusion to the story arcs of many of our favorite characters, Iron Man included. In Endgame, Tony has to snap one final time to bring all of Thanos' evil plans to an end, and the snap itself is what ends Tony's life. What does the Infinity Gauntlet snap actually do? And does the movie's implied physics fit with the real world? Can we figure that out? I think so! First of all, what is in a snap? Well, helpfully, in Avengers Endgame, Professor Hulk points out that when the Infinity Gauntlet snaps, it releases a tidal wave of radiation, most of it in the gamma ray portion of the electromagnetic spectrum. Gamma radiation, denoted with this symbol here, sounds scary, and it can be, but gamma radiation is just light, like visible light is light or radio waves way down here are light. What makes it potentially dangerous for human beings is that it also has the shortest wavelength and the highest energy among photons of light, and that high energy can do weird stuff to the human body. I need to buy new gloves. How much gamma ray energy are we really talking about, though? Well, helpfully again, Mr. Stark has an offhand comment in Avengers Endgame where he says the gauntlet, equipped with all 6 Infinity Stones, could power a continent. Hey Friday, why don't you pull up the annual power consumption from North America, please?
Sure thing, science boy.
You know my name. The problem with a power value like this is that power is defined as a unit of energy per unit of time, joules per second if you do all the conversions here. So we can only really figure out how much energy is released during a single snap if we all agree on how long a snap takes. How long does a snap take? Maybe about the time it takes you to blink? Sure, let's say about 1/10 of a second is how long a snap takes. Hey Friday, why don't you hit me up with that sweet multiplication?
You can't just take 10% of that?
I mean, I could, but doing the math ourselves and converting, we get around 54 billion joules worth of energy for a single snap if all of our assumptions and calculations are correct. Now, if 54 billion joules worth of gamma ray radiation sounds bad, that's because it would be. Nuclear bombs and dangerous radiation have been linked in our minds for a long time, but when an atom bomb actually goes off, only a small minority of the energy goes into the kinds of radiation that we've been talking about. The majority goes into the blast itself and the heat generated. Still, atomic bombs like the one dropped on Hiroshima during World War II release trillions of joules worth of gamma ray radiation when they explode. Our Infinity Gauntlet snap would have about 1% of this kind of energy. That sounds small, but 1% of a trillion is still a lot. And remember, it is all happening literally this close to Tony's face, a sphere of radiation extending outwards in all directions. It would expose Tony to more radiation than any human has ever experienced at one time. What Iron Man would have experienced next is the worst case of radiation poisoning in history. Radiation is all around us all the time, constantly hitting our bodies. There is the more harmless radiation, like the visible light hitting the back of your eyeballs from the screen you are watching me on right now, and there is the more harmful radiation that comes from background sources, like cosmic rays from space and radioactive atoms in the food that we eat and the air that we breathe. We really only concern ourselves with measuring how much of that dangerous radiation we are absorbing. So here is a graph of that measured in millisieverts, which just gets at how much radiation our body is absorbing over time. Now, here is how much the average person in the US absorbs per year. Here is how much radiation you would absorb if you got a single abdominal CT scan. Here is how much you get after 6 months aboard the International Space Station, cosmic rays and all of that. And here is how much you would get on a realistic trip to Mars. Oh, and here's how much you get from eating a single banana. Tony, though, would get a lot more exposure than this. I cannot even show you on the scale of this graph how much radiation Tony would be exposed to. If these are millisieverts, 1,000th of a sievert, then he would be exposed to billions of those. And this is why the Hulk volunteered to snap the gauntlet the first time. Normal humans simply aren't evolved to handle this kind of radiation. Wow, I should get that looked at. And my glove budget's getting too big. As you have probably guessed by now, the snap radiation levels that we calculated would in fact be 100% lethal. But what would happen to Tony next? Would the effects that we see in the film fit with what we know happens during extreme radiation poisoning? As we've gone through many times on this program, the dangerous radiation we've been talking about is more specifically ionizing radiation, and it's dangerous because it has the energy to rip electrons from atoms, and once that happens, they become ions, ionized, and these new ions can interact with our bodies in different and potentially fatal ways. This is how much radiation your body absorbs every year just from background sources. You don't even notice. Multiply this value by a few hundred, and now you are at the radiation exposure limit for astronauts over their entire career. Nothing crazy happening to their bodies, but there is now a slight increase in their risk of cancer. Bump this up again, and now things are getting dangerous. At 4 to 5 sieverts, an acute exposure, a very, very quick exposure, will lead to widespread cellular damage, cognitive impairment, extreme nausea and vomiting setting in within a few hours, and 50% of untreated people who are exposed to this kind of radiation will not make it. Even with treatment, an exposure to 10 sieverts or more will lead to death in 100% of people. Organ failure, extreme lethargy, and death within a few days to hours to minutes. Using our numbers, during a short infinity snap, Tony might be exposed to more than 1 million sieverts, obviously a beyond lethal dose. This could plausibly lead to the extreme lethargy and confusion and very quick demise that we see in Endgame. And the scary thing about radiation exposure like this is all it takes is a brief flash of it. Flash. If this makes sense and what it could do to Tony makes sense, what about the flash of light that the snap makes? Could that be more than artistic license too? On May 21st, 1946, physicist Louis Slotin was working at the famous Los Alamos National Laboratory in New Mexico, and on this day in history, he decided to do something extremely dangerous, what Richard Feynman called tickling the dragon's tail. Slotin was experimenting with a core of radioactive plutonium, and he was performing so-called criticality tests. The idea here is that you can make a subcritical piece of nuclear material go instantly critical if you surround it with enough material in the right orientation to reflect its radiation back in on itself and start a chain reaction. On that day in 1946, Louis Slotin was doing this with 2 halves of a beryllium sphere, lowering those halves around this plutonium core. But instead of some complicated and very careful apparatus to do this, he was just using a screwdriver to keep the 2 halves of the sphere apart. And then the screwdriver slipped. The core went instantly critical before Slotin could separate the sphere, and those who were there that day reported a flash of blue light and a wave of heat. In that instant, standing literally this close to the assembly, Slotin had received a dose of 21 sieverts and died 9 days later. Those who were in the room with him reported that he said after this flash of light, well, that does it. It's a morbid tale, but it actually provides something useful for our purposes. The Infinity Gauntlet, if it is releasing radiation and that radiation is smashing into the air around it, it could produce a flash of light. It doesn't just have to be movie magic, it could be deadly serious. This is all very sad and somber, but let's make Tony proud and go one step further. How could you make an infinity snap safer? Everything does look cooler in these. There are 3 simple ways to increase your radiation protection. Friday, tell them.
You said simple? Can't you just tell them?
Can I just tell them? What's the point of having cool technology if you're not gonna use it, whatever? The first protection is time, and that should be obvious. If you are exposed to some source of radiation for some period of time, the less time you're exposed, the less exposure you get, which makes sense. But how do you shorten a snap if we want to get less radiation from it? Now, I guess it has to be a snap because of the movie, but would an infinity clap be faster? Is that faster? Nah, that just looks dumb. The point is, the math is simple. The less amount of time that the infinity power is active, the less radiation you get. You could also increase the distance between you and the Infinity Gauntlet when it snaps to decrease the amount of radiation you'd receive from it. Radiation coming from a point source like a light bulb or gamma rays from our Infinity Gauntlet here will shoot off in all directions in a sphere and decrease in intensity as it does so. In other words, it follows the inverse square law. As the gamma rays shot out of the Infinity Gauntlet during the snap in Endgame, they would spread out, and per unit area, their intensity would decrease proportional to 1 over the square of the distance. You can see these areas getting much larger as the distance increases, so the intensity decreases very quickly if you get further and further away from the Infinity Gauntlet. So if you could figure out a way to take the Infinity Gauntlet and move it to a distance, and then snap it from there, you would increase your chances of not being totally Iron Man'd. However, with our numbers, you would have to be hundreds of meters away from that thing. Finally, we could shield ourselves from the radiation of the snap. The radiation that we've been talking about so far can be frightening, but some of it can be stopped in its tracks with the right shielding, kind of like I'm stopping the light from bouncing off of my face and making it to your eyeballs just with a sheet of paper. Wow. The problem with gamma rays is that a simple sheet of paper would not be enough to stop them. It would be enough to stop alpha particles, for example, and a thin sheet of aluminum would be able to stop a stream of electrons, but gamma radiation by its very nature is extremely penetrating. You would need a wall of lead or water just to reduce your exposure, and you're still probably not going to stop all of it. Maybe Tony could come up with some ultra-thin material that's a metal that can go into his suit that could stop all that radiation, though? If he could, then you can imagine the perfect non-sacrificial scenario where Tony has the gauntlet with all the Infinity Stones on it, and then he uses his Stark nanotech to shield himself from the snap, holding the gauntlet as far away from him as humanly possible, and then trying to snap as slowly as possible? That would be everything he could do to reduce his exposure if he still had to have the gauntlet on his hand, but I guess that just wasn't possible for him. It just was never gonna be his endgame.
Ooh, dramatic.
I was trying to be like emotional and cool. Hey, shut up. You do it. So, what really happened to Iron Man? He heroically exposed himself to more ionizing radiation than any human in history in order to finally defeat Thanos and save the entire universe. And if it really went down this way with gamma rays and radiation, not only would that radiation close Tony's story arc reactor, it would create a flash of light just like we see in both Infinity War and Endgame. In terms of coming up with an emotionally satisfying and scientifically accurate send-off for Stark, the Avengers assembled a decent explanation.
Because science.
So we mentioned shielding last, and if you think back to Endgame, there's a problem with shielding, specifically when the Hulk snaps the Infinity Gauntlet himself. Everyone is standing in the room and they kind of brace for the impact of the snap, and like Hawkeye just kind of like goes like, and Iron Man puts his suit on, puts his shield up, and people are like, But if it's really gamma radiation, every human non-shielded by a giant wall in that room would have also not made it. I would have loved that ending, not 3000. Thank you so much for watching, Birgitta. If you enjoyed this episode, follow us here on social media and you can suggest ideas for future episodes, and hey, sometimes I use them. Also, the Science of Mortal Kombat series is now live on our channel. 6 episodes, 6 behind the scenes episodes. Wow, it was a lot of fun. You're gonna wanna see us punch stuff and burn stuff and smash stuff. So give it a smash that view button.